will be a view on the question of sort of, are there winning strategies in particular kinds of games? And I would guess that to most people in the audience, the natural kind of question here are, how strong an axiom system do you need in order to prove the existence of such winning strategies? My background is more in computability theory, so the question that I'm going to look at is, how hard is it to actually construct these strategies, which of course means that I have to restrict myself to such settings where they actually are there in the first case, but one can then kind of do a lot of more fine-grained analysis of what is going on here. I will start with a brief background on Weihrauch reducibility, which is just the formal setting for asking these questions as in how hard is it to construct things that you can't actually construct. And then I will probably spend most of my time looking at the strengths of the existence of winning strategies in the for games with just a finite set of a finite set of moves at each time, and the winning condition will come from the House of Kuratowski hierarchy just over the open sets. That part is joint work with Stéphane Leroux, also from the ULB in Belgium. I will then remark briefly on how looking at the kind of the computational strengths of these particular kind of games relates to games of which are slightly longer, namely games of length omega times 2, and if time permits, mention some very recent results of Takayuki Kihara from Berkeley, then looking at countably branching game trees. So, when we want to compute with more complicated things such as games, strategies in games and so on, we need a sensible notion of computation. So we are going to start with bare space, since we know how to compute with elements from bare space, and then we will fix suitable partial surjections from bare space onto the set we are actually interested in, and just call that representation of that particular set. And of course, you need to make sure that your representation sort of matches your intuition about what that space actually is. For those settings we are looking at, it will be rather straightforward. And then we can relate partial functions on bare space to multi-valued functions between these represented spaces by just demanding that this diagram commutes. So we have sort of some idea of here are elements from X, and we want to obtain a suitable element of Y linked to that X somehow. And what we actually do under the hood is that we get a code for the X, and we need to find some code for some Y matching that X. And then such a multi-valued function between represented spaces, we can call it computable if it has a computable realizer, continuous if it has a continuous realizer, and so on. For those of you who do not particularly enjoy computability theory, you can replace every statement of computable by continuous, and you get something which is still true. And for those spaces I'm going to talk about where you have a clear idea what the topology on that space should be, it's then actually continuous with respect to that topology. I'm probably going to talk about spaces where you do not know what continuity should mean, but there it will kind of just come from the representation like this. Now the idea of Weihrauch reducibility is just that assume we have a multi-valued function g, which we can use as a black box. We can just use it once, and all the rest of the things we're doing will be computable transformations, then we say that F is Weihrauch reducible to G. So this is a really fine-grained relation. We can distinguish using a certain statement once from using it twice, and we can distinguish using it twice in parallel from using it twice sequentially, and so on. But there are actually some kind of meaningful statements to be made there. By looking at the relation on the equivalence classes, we obtain a distributive lattice. The Cartesian product, which you can naturally extend to represented spaces, gives us a kind of one more operation on this lattice. The Medvedev lattice embeds into it dually. I think we can skip that. The fundamental idea is that if you have a mathematical theorem which has this form for all x and x, there is some y inside y such that if some condition happens to be true, then y is in a particular relationship to x. I'm not saying anything about the complexity of d and t here. That's just the general form. But we can understand that as a multi-valued function from x to y, where kind of the difference over x being inside the space x and x satisfying the property d is that x being small x being a member of big X is telling us how to code x, what information we have. That d is true for the interesting cases is just true, but we don't have any information about that in detail. And then sort of the Weihrauch degree of the multivariate function obtained from the theorem tells us a bit, tells kind of what the constructive content of the theorem is. It looks a lot like constructive reverse mathematics, but since we can use theorems only once, it's different. In particular, it's not actually a model of some intuitionistic logic. I will need one particular operation quite often to actually formulate the results. So I'm using the I'm going to use that one element of Baire space can code in an entire sequence of elements in Baire space. So we can look at the partial map, which maps a sequence which happens to converge to the sequence it's converging to. We can then define a jump on represented spaces. So the points which are inside x prime are the same points x has, but rather than getting a proper code for a point, you could just get some sequence converging to some code, but sort of you don't know how fast it's converging and so on. You just have the guarantee that it's converging. So you have really very little information in the space x prime. And now if we have some particular function, or actually multi-valued function, we can get a whole hierarchy of sort of more and more complicated problems. Why are they more complicated? Because we have less information. We have less information on the input, a sequence converging to a sequence, converging to a sequence, and so on, converging to the actual code for the thing we are looking at. Now, two particular problems to then use this operation on. This is the limited principle of the limited principle of omniscience. I think going back to Heiting, in order to prove that certain things are definitely observed from a constructive perspective. That's really just the characteristic function of the constant zero sequence. And in order to actually solve that, you would need to kind of know the entire sequence at some particular moment in order to then be able to answer. The other problem is, given a closed subset of Cantor space, which happens to be non-empty, find a point inside that set. So how are you given a closed subset of Cantor space? You are given an enumeration of its complement by just listing more and more finite words who are then building that one up. You obviously kind of can't solve that in general, because whenever you start to try to write the output, it could happen that some prefix of what you're currently writing is showing up in your input as something which is not inside that set. Here, however, we really need to look at this as a multi-valued function, because for Cantor space, it happens to be the case that if there is a unique solution, we can actually compute that one, because we then just wait until all but one word of a particular length have been are no longer possible by compactness, and then we know that. Right.
Sorry, why is that the reason it needs to be multi-valued?
Well, because that particular multi-valued function is not computable. Well, I'm ignoring some details here, but more or less for this particular function, you can show that if it were equivalent to a single-valued function, then it would have to be equivalent to this particular single-valued function, where you just restrict it to sets which just have one particular point in it. But that thing is a computable thing. Weihrauch reducibility preserves computability, so it can't be equivalent to anything which is not multi-valued.
Okay.
Right. Games in the difference hierarchy. I'm going to define the difference hierarchy by particular operation on point classes. So we have some collection of subsets of Cantor space. We take a collection of incomparable finite words, and then for each word we pick one set from the original point class, glue it together, takes a union, and that gets us this larger point class D of gamma. And if we start with just the set containing only the empty set, and then build this up by always taking the complements of the things we've put in so far, and then use this operation D, we just get the usual finite levels of the Hausdorff-Kuratowski difference hierarchy. I'm going to only state things for the finite levels. One just has to do some careful ±1 arithmetic and more complicated ways to define the problems, but things work for the infinite levels too. Right. Now, for a particular point class, I'm going to look at 3 computational problems. The first is taking in a game where the winning set of the first player is just coming from this point class gamma, and the output will be pairs of strategies, such that the player who has some winning strategy is actually going to use some winning strategy. Since the other guy is knowing that he's going to lose anyway, he can play however he likes. Then win is asking who is actually winning, and it makes sense to point out that sort of knowing who is winning doesn't tell you how that person is going to do it. And even if you have this pair of optimal strategies, you still don't know who's actually winning with that. So these two are different problems at first. And then in the third case, we're going to restrict ourselves to only games where we know that a particular player is going to, can win. The question is how. And the fundamental result is that first looking at this task of to find these optimal strategies. As your winning sets go up in the Hausdorff-Kuratowski difference hierarchy, you always have a closed set of optimal strategies described with weaker and weaker information, because rather than actually knowing the set, you only know a sequence converging to it. If you're on the first level, or you have a sequence converging to a sequence if you're on the second level, and so on. On the next slide I have some consequences which may make more sense, and likewise to decide who is winning, rather than getting the sequence where we have to say whether it's zero, whether it's constant zero or not, we get only stuff converging to it. I don't think I can go into the proof of that, I'm afraid. So for computability theorists, classical consequence is that any computable game, meaning just that there's a machine which is kind of doing the in and out thing in the straightforward way, has a winning strategy such that the jump of the winning strategy is computable relative to the nth plus first halting problem, and this is really more or less as much as you can say, since there are computable games which have only very complicated winning strategies, in particular no computable winning strategies, and so on. This is so. Yeah, we can list games in such a way that if we know who is winning which game, that actually codes some jump of the halting problem. And maybe a more theoretic version is that there are that we need to climb up the bear hierarchy with the strengths of the functions mapping games to strategies as our games climb up the Hausdorff-Kuratowski difference hierarchy. And this latter thing is what one can then use to reason about games of transfinite lengths. First, the details are all on the archive, and several key constructions have been taken from a paper by Takako Ninomoto, Mitzalam, and Tanaka. Right. Here I'm just going to show you one statement and maybe draw a bit of a picture. So we keep with the to just having a finite number of moves at each particular time, and now we can look at either games with delta 0-2 winning conditions of length omega times 2, or at delta at delta 1, so rel winning conditions of length omega, and we can computably transfer back and forth. Maybe for that I'll just draw a short picture. So if you have your long game, then of course you can ask kind of you can just ask for each particular history of what happened in the first omega rounds, what you get down here is just a game of the same type, but now no length. Well, now kind of here you're just getting yeah, here you're just getting some game of the same type, which is no shorter, and you can play the whole game in a good way by asking for each game down here, can I win this game, and if so, how? And then, can I reach some point here from which onwards I'm going to win? And if I can do that, then I can win the whole game by first reaching some history of length omega that I can win, and then win that history. Since if each game down here has a winning condition somewhere in the has a delta 0 2 winning condition, our result just shows that the winning condition of this, how to play the first round, is just some Borel game. Vice versa, if you have some particular Borel game, then then the next direction of the result that we have shows that for the Borel winning condition you have here, you can essentially find an extension with the property that now the winning condition of the entire thing is much lower, and you can win precisely those histories here in the long game, which you had, which you just win right now in the short game. So that's the idea how you go back and forth here. And this may not be that interesting to a community of kind of for people who would just say, well, Borel that since we know that since delta 1-1 games just have winning strategies, it's not telling us that much new, but the same kind of technique would work for larger classes of sets where we can just ask, okay, we can do this if we know how complicated the map from games to winning strategies is, then we can use that to look at longer games. A really brief remark on what happens if we drop this assumption of only having finitely many moves at any particular time. Here the principle we will need to look at is just given a closed subset of bare space, find some point inside that set where we're getting the set once more just by some list of the finite prefixes of its complement. And here the restriction to sets of just one single point is no longer computable. It's actually quite hard. This unique closed choice has just these strands of delta 02 that for counter space, or delta 01 that on bare space. But now we see if phenomenons we really do not have on counter space. So if we know that the guy who is trying to reach the open set can win, then we can compute a closed singleton such that the singleton contains an winning strategy for him. If we know that the guy with the closed winning set can win, we can compute a non-empty closed set of strategies which can actually win. However, now we would ask, well, if we can we compute sort of one closed set of optimal strategies of one guy and one closed set of optimal strategies of the other guy, and just combine these points to get such a pair that whoever can win will win? And the answer is not that easily. So being able to pick a point from a closed set does not actually let you pick an optimal pair of strategies in such a game. And here we actually see that if you have two games and you're supposed to solve both of them, that's harder than just having to solve one game. Whereas for a finitely branching games, you can have countably many games and you can solve all of them just in one go. And here that somehow breaks down. And actually,
well, you started at the beginning.
okay, I sort of used the clock, and so I'm actually over already. If you want me to explain any proof, I can use that if you want coffee.
Andreas, I have a feeling you had some papers long ago, some similar.
Yeah, but I also have a question about something that's not quite that ancient.
Oh, right.
Namely, you mentioned that in connection with this Weihrauch reducibility, you're only allowed to use the data once, and that this is what interferes with getting a Bauer algebra. That sounds a lot like what happens in linear logic, so I'm wondering if there's a connection with that rather than with intuitionistic logic.
Yes, so sort of the current idea is that sort of Weihrauch reducibility should behave a bit kind of like linear, like intuitionistic linear logic. It's sort of not that simple that say it would just be say if you look at the algebraic structure we have on Weihrauch, we see plenty of things we would expect to see from that perspective. However, we also have, for example, rather than just one, we have actually multiple exponentials, because we could have something like you can use this an arbitrary but finite number of times. You can use it in a pre-specified finite number of times. So it's a difference whether you're just going to stop eventually or whether you'd say how often you're going to use it. You could have something like that. You can use it countably many times with all independent questions. Each of these operations kind of matches the exponential. Probably the disappointing part is that we don't have that we have very few implications. We have two commutative ANDs and a non-commutative AND, and only the one-sided implication where the non-commutative AND works. All the others don't exist. So yes, there is some connection. It's complicated and not a very precise one.
Is the non-commutative and some kind of sequential use?
Exactly. So it's you first use this one, and then you can use the output of that one to make your next question.
Oh, I should probably comment on what you were referring to.
Yes.
So the ancient work of mine was looking at something somewhat more general, where you're looking at arbitrary, essentially recursive games, and saying that winning strategies are hyper-arithmetic and you can't get any better than that. This, looking at things in the difference hierarchy, is sort of related to that, but in fact also related to a somewhat older theorem of Rabin, where the result was just that you don't always get recursive strategies. And I think his example was somewhere like maybe the second or third level of the difference hierarchy.
Yes, so sort of the pointwise version of this result is essentially saying it's hyper arithmetical, but you don't get more.
With regarding games on bare space,
Yeah.
there's been a lot of work done very low down in the definability hierarchy, because delta 0 4, delta 0 5, and then you're going past second order arithmetic already. But beneath that, there's been quite a bit of work done on very fine differences, even more than just the difference hierarchy,
Yeah.
or determinacy for these various fragments of delta 0 2 and sigma 0 3 and so on. Have you guys looked at anything much beyond what you've shown us today?
No, because this one here is sort of, I think, 2 or 3 weeks old.
Well, then you've had a good 2 or 3 weeks.
Yeah. Well, kind of. I mean, here we are essentially quite a good deal behind what people in reverse maths have been doing, and the reason for that is essentially the last line. Since we distinguish using something once or twice, and since quite often that doesn't actually matter, because many nice theorems have this property that if you can use it once, you can use it any finite number, and so on, which of course makes writing down proofs much easier. If you're inserting a non-uniform case distinction, you can actually go back to the left. But we're still struggling about the details here, and kind of looking at more complicated fragments, I think, is still a bit beyond our current reach.
Well, lunch break is happening now, so let's thank the speaker again. This is my message to the audience.